Welcome. We're the Adversarial Techniques for Face Recognition Models research team. I am Abdel Cortez, and today I am joined by my colleagues Remy Dotero and Joshua Matos. Face recognition systems are a type of biometric authentication that seeks to use an image or some other form of data that represents someone's face to identify them. Most of these models work using some type of machine learning, and the problem with that is that those type of machine learning models have been proven to be very vulnerable to specific types of adversarial attacks. And our research focuses on developing and researching these adversarial techniques aimed at fooling the face recognition models. One of these techniques is the one pixel attack, which is an adversarial attack that seeks to change the image's label by only changing one pixel. If you can look at the examples on the right, you see that the one on top is the original image, which was classified by the model as a frog. And then after adding one pixel, it was classified as a deer. This attack works using a special type of evolutionary computation called differential evolution, and it chooses this pixel through this evolutionary process. And it is a black box attack, meaning that we only need to know the inputs and outputs of the model in order to produce this attack, meaning that we don't need to know any of the inner workings of the machine learning model. So the gist of how differential evolution works is that you first randomly generate an initial population of pixels, and then you pass them through this evolutionary process where in each iteration, you select a few different pixels, you mutate them together, and you compare the mutated pixel versus the original pixel, and whichever one has a higher fitness is the one that remains in the population. And we determine fitness using the machine learning model, and seeing how much it changed the output of the model. And then once we've gone through this evolutionary process enough times, we're able to produce a pixel that completely changes the output label of the image.
Another attack that we're developing is the visible light based attack. This attack explores the concept that in typical examples in face recognition, we desire a classification function being robust to projected light. To test this robustness, we generate a pattern based on transformations that rely on invariance objectives. In other words, invariance with respect to some transformation of the input, such as translation, rotation, scaling, etc. After generating our pattern, we use the face recognition system in black box setting to recognize the subject face and to later select a target one. The pattern is then projected onto the adversary's face to either impersonate a target or evade the recognition. A more detailed explanation is presented in this part. With respect to the experimental setup, we're going to use the BG2 dataset to take input of the subject face and target face for the subsequent parts. Then we use a base face detection and landmark estimator for automatic position calibration. We start the process of generation of the perturbation by averaging the different invariant adjectives transformations applied to the subject image. Each transformation is assumed to be equally likely, therefore it has the same weight in the average. Then we sum this average and temporal image are clipped to 255, representative of the maximum value in an RGB scale. We compute the distance using a metric scale, and then we run the process until the predefined number of steps or the threshold of this distance is reached.
Hello, today I'm going to talk about GAN behaviors in Face ID systems. So my initial part was to understand GANs. GANs are a neural network machine learning architecture designed by Goodwill and his colleagues back in 2014. Basically, it's a generator that tries to imitate or create images similar to the ones in the training set, and it has a discriminator that tries to say if the images are part of the training sets or are generated. So we're trying to understand the properties that GAN images have on Face ID system. We want to know if the Face ID system will accept any GAN generated image or if it will deny every image that is generated by the GAN. Also, if we have a database created by GAN images, will other GAN images be allowed to will be accepted or will be denied? It's something that's really interesting and part of my research. Also, GANs they have like intrinsic properties such as artifacts and fingerprints. So the artifacts are, as you can see in the lower right corner, we see a man that has three red circles. In the three red circles, we see the artifacts. So we see like a blob of meat. On the right of the right man, we see an ear that is deformed and an ear that is mixing. Also, we see in the top right, we see two squares, one that is green and one that's like a cross. The green is a GAN-generated fingerprint, so it's a noise that is intrinsic for the GAN-generated images, and we see the cross. So the importance of this is that these things are, they distinguish real images from GAN-generated images. So we want to know if we can filter those and if we can fool any Face ID system, or we can see how this Face ID system respond when we have images such as this one cleared from the GAN's artifacts. So the end goal for research, right, is to understand how the three implementations of the adversarial attack work in the system of the Face ID and how this Face ID system uh, are compromised or how they behave when encountering these three problems. In the case of Fremute and Abdil, both of them attack existing image, and in my case, I generate new images for the Face ID to recognize. So in the case of Adil, Adil has like a prototype of the version of his attack. In my case and Fremute case, we haven't had yet developed a prototype for the case. So in the end, we want to create like a system, and we want to create like a flow of attack that can test the ideas on the Face ID system. And these are the references of our research.